These are the 6.4 part 1 video notes, and we're going to be looking at the graphs of the sine and the cosine function. So we want to think about these functions as graphs now, and we're going to be taking our information from the unit circle. We're going to take these xy values, and we're going to turn it into the xy coordinate plane. So we're going to kind of flip this around, and we're going to think about this in a completely different manner. I'm going to turn all of my trig functions into functions, and we're going to graph these as functions. So I'm going to consider this as y is equal to the f of x is equal to the sine of x, and y is equal to f of x, which is equal to the cosine of x. So these are two separate functions which we're going to consider, and we're going to figure out how to graph these, just like we'd graph anything else. Now in this case, our x value is actually going to be a theta. And you might still be used to working in degrees. You might like working in degrees a lot more than radians, thinking about your thetas as 30s, 45s, etc. But we're going to think about this purely in radians. Because when we do trigonometry, we like to think about these in radian values a lot more. The radian values, the angles make much more sense. They're related to what's actually happening in the circle. They're related to the ratio of the diameter and the circumference. We like radians a lot more. Now, we have to know about the period of sine and cosine functions before we start knowing how to graph these. And what is a period? Well, a period means that they start repeating themselves. How do we know that they repeat themselves? Well, let's think about a random angle. Let's think about pi over 4. Now, pi over 4 has the coordinate points of root 2 over 2 and root 2 over 2. Now, what about the angle 9 pi over 4? 9 pi over 4 also has the points root 2 over 2 and root 2 over 2. Well, that's because we can break down 9 pi over 4 as 2 pi plus pi over 4, because 2 pi can be turned into 8 pi over 4. So now we've got these two angles, and both of these angles end up terminating in the exact spot. So we've got pi over 4, which looks like this, and then we've got 9 pi over 4, which looks like that. They end up terminating in the exact same spot. They have the exact same amount of revolution from that positive x-axis, although 9 pi over 4 rotates a full 360 or 2 pi radians before it goes that pi over 4. But they terminate in the exact same spot on the unit circle and terminate at that point root 2 over 2, root 2 over 2. Well, that means that the sine of pi over 4 is root 2 over 2. We know that one well. And the sine of 2 pi plus pi over 4, or 9 pi over 4, is going to also be root 2 over 2. Cosine, it's also going to be root 2 over 2. The cosine of 2 pi plus pi over 4 is also going to be root 2 over 2. So that means every 2 pi values, it starts repeating itself. We have the same cosine and sine values every 2 pi values. It happens repeatedly over and over and over. And what we do is we call this a period. And all trig functions have a period. It means that it's cyclical. It happens over and over. And we've seen this before. We've started looking at this. We might not have had the words for it. We might not have really been able to describe the phenomena. But as we went through and we found the sine and cosine, tangent, cosecant, all those values of these different angles, we realized that once we start repeating it, it kind of matters what quadrant we're in more than anything else. That all the magnitudes will be the same, and the quadrant changes the sign. Well, we don't have an infinite number of quadrants. We only have 4. And these are circular, so they start rotating. They go over and over. It's just kind of like how when you run on a track, how you're kind of looking at the same sites over and over again. And as you make those turns, you might change the sites slightly, and you might look at them a different way, but you're still looking at the same things over and over. So we kind of have these cycles happening, and we're going to start applying it. So when I graph the sine function in these notes, I'm only going to graph from 0 to 2 pi, because it will start repeating itself. I have some screenshots from Desmos to help us look at what that is, but we're only going to look from 0 to 2 pi. Now on this slide, I'm actually going to go ahead and create a table of values for sine of x and cosine of x. So I'm going to say f of x is equal to the sine of x for the first one. And when I make a table of values, I'm only going to think about my quadrant angles. So I'm only going to think about 0, pi over 2, pi, 3 pi over 2, and 2 pi. Now, the sine of 0 is 0, sine of pi over 2 is 1, sine of pi is 0, sine of 3 pi over 2 is negative 1, and sine of 2 pi is 0. We've learned all of these before. This is from the 6.2 notes. You might have to go back, watch those again, look at how I figured out those quadrant angles. But we've known this, and we've known this for a while, that this is just the sine value at these quadrant angles. Now I also want to know for my cosine, we're not going to graph that for a few slides, but we might as well make our table of values now. I've got the cosine of x, and I'm only going to think about the quadrant angles. I'm going to think about x, I'm going to think about y, 0, pi over 2, pi, 3 pi over 2, and 2 pi. Cosine of 0 is 1, cosine of pi over 2 is 0, cosine of pi is negative 1, cosine of 3 pi over 2 is 0, cosine of 2 pi is 1. So we can kind of see that they're very similar in their patterns. They both have zeros, they both have ones. They're a little bit off. We're actually going to learn how we could rewrite the sine graph to lie directly on top of the cosine graph, or the cosine graph to lie directly on top of the sine graph, but that's going to be a little bit in the future when we start looking at some phase shifts. But these are going to look very, very similar, frighteningly so. Now, why did I only do the quadrant angles? That's because these are nice values. I could do pi over 4s, I could do pi over 6s, I could do pi over 3s, but trying to like estimate where a root 3 over 2 is, or estimate where a pi over 3 is on a graph is a lot of work, and it's kind of hard. So mathematicians kind of agreed that when we think about these graphs, we think about them at their quadrant angles, because that makes our life easier. And then again, we have graphing software, we have Desmos, we have TI-83s. If we're really looking for detailed graphs, we're going to pull those up. This is to get an understanding of what these graphs are, what shape these graphs make, and why do they make these shapes? What is the cycle? We're really going for like a hard understanding of what this trig is doing, as opposed to like a nitty-gritty, let's make sure this graph is super accurate at every single point. You're going to drive yourself crazy. It's tedious that way. Thinking about your quadrant angles gets you everywhere you need to go, knowing that everything's occurring within those quadrants. So now that I have this table of values, I'm going to copy it and I'm going to paste it for my sine of f of x is equal to sine of x graph. And I have xy coordinates now, so I know that I've got this point 0, 0. I've got this point pi over 2, 1. I've got this point pi 0. I've got this point 3 pi over 2, negative 1. And I've got this point 2 pi. I guess it would also help if I established that I'm scaling this graph by 1/3. I just kind of jumped the gun on that. I want to be able to see this graph well. And so I go through, I get to the point 0, 1, I come to the point pi 0, I go here and I go here. And what this ends up doing is creating this shape called a wave. We actually call this a sinusoidal wave. This appears all the time. This is oscillatory motion. This is pendular motion. If you think about circular motion, this is applied all the time in physics. This is something that is huge. We can think about this in terms of orbit of the planets. I even recall when I was 13 years old, my dad was building a deck, and I showed up downstairs, and he had all this math out, and I was like, "Dad, what are you doing?" And he was building a shade structure for the deck. And he said, "I'm studying the sinusoidal patterns of the sun to try to figure out how to maximize shade during the summer." And he took a class on that in college. It was heating and cooling systems. They look at how the sun moves in regards to the earth, and they use those sinusoidal patterns in order to calculate the amount of shade. So when people are building houses in Wisconsin, a lot of architects, engineers, they pay attention to the sinusoidal waves to maximize sunlight in houses, reduce heat costs during the winter, etc. So this is something that's it's applied in a lot of different ways that you might not think about right away, but this is huge. This is really, really big information here in the sinusoidal wave. Now, the thing that I like to do when thinking about the sinusoidal wave is break it down by quarters. And I've got 4 quarters, and here's what happens in each. In quarter 1, I move from my point 0, 0 to my point pi over 2, 1. So I move from a 0 to a peak. My second quarter, I move from a peak back down to a 0. So I'm using my zeros as breakups for all of my quarters in some way. My next one is from that 0 to that valley, or that negative 1. So I've got another quarter here. This is my third one, going from 0 to that negative 1. And then I've got my final movement from that 0 or from that valley back to that 0. So we can see that at each 0 value, I've got a quarter starting or stopping. And it's from the 0 to the peak to the 0 to the valley, and then the valley back to the 0. So I've got these 4 quarters in my graph, and this is something that's going to make me doing my period shifts a lot easier. So I'm going to change my period, and that's going to make my life quite a bit easier when I do this. All right. Now, this is the graph of the sine function, and I have this from Desmos. I want to show you how this is cyclical, how it repeats itself, so you can start seeing that this wave just goes on and on and on and on and on and on and on. I've got my table of values from Desmos here too to prove that I have real values here. I even started showing you the negative values a little bit to show you how this same cycle would repeat in the negative direction too. So everything here is really solid to me. I'm really happy with how this graph is looking. It's just kind of going in the right direction. Everything's working out really, really well for me. Now, the vertical stretch factor, or everything here is working out well for me. It looks really good. This is what the sine graph looks like when it repeats over and over. Now, the vertical stretch factor, if you have a vertical stretch factor, it appears as a coefficient outside the trigonometric function. So for example, we've got f of x is equal to 3 times the sine of x. So that's outside of it, and it changes the amplitude of the graph. Now, what is the amplitude? The amplitude is, let's say that I have a graph that looks like this. Like, let's say that's what the sine function normally looks like. If I make the amplitude larger, now suddenly the sine function looks like this. And if I make the amplitude smaller, the sine function looks like this. We're talking kind of about the distance from our origin, our axis, x-axis, whatever you want, to the peak or the valley. So that's what the amplitude is. It's the height of the wave. It's how tall it gets. And this shifts that because we're taking the sine and then we're multiplying that sine by 3. So if we want to think about our original chart that we had, if I've got f of x is equal to the sine of x, well, what I'm doing is I'm kind of doing a transformation, and I'm multiplying the y values. Let's actually change this to a dot so it doesn't look like xy. I'm going to multiply my y values by 3. So now I've got a new table of values that I can create. I've got xy coordinates. I've got 0, pi over 2, pi, 3 pi over 2, and 2 pi. And it's still at 0, 0, but at pi over 2, I normally have a sine of 1, but I'm going to multiply that y value by 3 and get positive 3. At pi, it becomes 0 still. It becomes negative 3 at 3 pi over 2, and at 2 pi, it's 0 again. I'm going to scale this y-axis by, let's do 1.5s here, just for fun. So this is by 1.5. I still have this point 0, 0, but then at pi over 2, I would reach my point 3, pi 0, 3 pi over 2, negative 3, and then 2 pi 0, and then I have my sinusoidal wave that happens as I go through it. And that is how it would end up with that function. So that's just applying it as an amplitude of going up to 3, going down to negative 3, and then going through. So it has the exact same shape. We can see that it repeats its cycle over 2 pi. It still has a period of 2 pi. So I'm really happy with this. Now, this doesn't look a ton different from the previous graph, and it's also a little bit weird with how it's scaled. So we have to make sure we're paying attention to that y scaling. I can make any graph with an amplitude look the exact same as a graph with a completely different amplitude if I'm changing the scale. But if you go through and plug this in on Desmos along with plugging in the sine of x, you'll see how this looks the exact same. It just goes up a little bit higher or comes down a little bit lower. Now we're going to apply that exact same principle when I'm doing the negative sine of x. I'm going to put my table of values. So I've got my table of values here. When I do my transformation, I'm multiplying my y values by negative 1. And I'm actually not going to make my table of values here because this is straightforward. Everywhere where there's a 0, it's still going to be 0, because if you multiply anything by 0, it's still 0, so that doesn't matter. And that pi over 2, where it was positive 1, is now going to become negative 1. We'll actually scale this graph by 1s, so we're going to keep this normal. So we're scaling this graph by 1, so we're keeping it normal. I've got that pi over 2 negative 1. I've got that 0, pi 0. I've got 3 pi over 2 positive 1. And then it ends up creating the same shape, but now it's just kind of upside down. If we think about this is the exact same transformation rule that we learned all the way back in October. We're reflecting it over the x-axis, so that means anything that was a negative y value becomes a positive y value. Anything that was a positive y value becomes a negative y value. So we're just shifting it. We're flipping it upside down. It looks very similar, should have the exact same shape. Whenever we're working with sine and cosine, always should have this wave shape. It might change where it starts, might change which direction it goes, but it's going to have that same shape regardless. So that's what I would do with a negative up front. It's just a reflection over the x-axis. You're just multiplying your y values by -1, and I don't even have to make a table of values there. Now, the function f of x is equal to the cosine of x. We've already done the table. The table for the cosine of x is all the way up here. So now we're going to go ahead. We're going to take that table of values, and we're going to put that with our cosine function. And I'm going to go ahead and plug in the values which we've already found. We've got a 0.01. Let's scale this y-axis by 1/2 this time. Got a 0.01. We've got a pi over 2, 0, pi -1, 3 pi over 2, 0, and 2 pi positive 1. So we can see that it does take 2 pi radians, but over 2 pi radians it will get back to that starting point, so I'm happy with that. And then I'm going to go through and I'm going to draw the shape. And it looks really, really funny because it doesn't have that same wave shape right now because we haven't really started repeating the cycle. If all I show you is one cycle of a cosine, it looks just kind of like a U. It doesn't look like a wave yet. But trust me, the cosine still has that sinusoidal wave shape. And you're going to see that on the next slide. I do want to emphasize that just like the sine, I can break this down into quarters as well. And it's still going to be based off of peaks to zeros and zeros to valleys and valleys to zeros. So my first quarter is from my peak to my first 0. My next quarter is from my 0 to my valley. My next quarter is from my valley to my next 0. And then my final one is from my 0 to my peak. Let's change the color. Let's not do purple twice. Definitely don't have any gray. So then that's my last quarter. So I've got these 4 quarters of the graph. I've got these graphs that are doing these things at these sections, and then when I get to my period shift on the next couple slides, we're gonna see, okay, what does this mean? What does this do? Why am I concerned with these periods? It makes doing a period shift, it makes changing the period of one of these graphs a lot easier if we know what's going on based on the general pattern of our graph. All right, so now I've got a desmos of the graph of the cosine function. We can see again that the table of values I've given to you that's just even what the graphing software tells us. We know that at 0 we have a value of 1. At pi over 2 we've got a value of 0, pi, -1, etc. It starts repeating this over and over, and now we can see that it has the exact same shape as the sinusoidal wave. It just starts at a different spot, so when we're graphing only from 0 to 2 pi, it looks a lot different because we actually see the wave shape with sine, but we don't get to see that wave shape with cosine, which is unfortunate from 0 to 2 pi. So I really wanted to make sure we had these Desmos screenshots in there so that way we could really see that it is the exact same shape. It is still cyclical. It repeats itself. It's just hard to see if we're only looking from 0 to 2 pi. Now, a horizontal stretch factor. Horizontal stretch factors appear inside of the trigonometric function, such as cosine of 2x. Now, this is a lot like what we learned in October. We saw horizontal stretch factors for the first time this fall, But what's different is a horizontal stretch factor in the fall was a lot like a vertical stretch factor. It was just kind of it was just a matter of where we chose to place it. We could make a function look the exact same depending on if it was a horizontal or vertical stretch factor. That's no longer the case. In trig functions, the horizontal stretch factor affects the period of the graph, and it either makes a shorter period for a stretch factor greater than 1, or a larger period for a stretch factor less than 1. And so we've got amplitude and period formulas here. So now we've got a general function that we have. Any sine or cosine function can be written by y is equal to a times the sine of omega x. And this would look like this in a homework or on a test. Y is equal to 3 times the sine of, let's say 2x. Or y is equal to 7 times the cosine of 4x. And what that means is your amplitude is the absolute value of a. We already learned that. That's kind of how high the wave gets. That's how tall it gets. That's how low your valleys are. It's your distance from your axis to your peak and your axis to your valley. The period, though, is a little bit different. We actually have a formula. So since our normal period of a function is 2 pi, to figure out any period shift, it would be based off of 2 pi over omega. So for this one, to figure out your period shift, you would do 2 pi over 2, and you would find that this one has a period of pi. For this one, you would do 2 pi over 4, because 4 is your omega value, and you would find out that you have a period of pi over 2. And that's how long it takes to repeat itself. So we're saying with this one, it repeats itself every pi radians. For the second one, it repeats itself every pi over 2 radians. Now, what does that mean? How do we actually apply this? Let's look at the function f of x is equal to the cosine of 2x. I'm actually not going to put down my table of values because I want to start thinking about my graphs as my quarters. I talked with Mr. Loudit about this. Mr. Loudit likes to think about this in the same way because as opposed to actually plugging in values and going through the tediousness of plugging in those values and figuring out how they work, it's a lot easier for me to just kind of think about the quarters and what happens. I'm going to scale my y-axis by 1/2 again. Now, the cosine of 0, without any phase shift, vertical shift, things that we're going to learn in the future, they always start at 1, especially with this amplitude. I've got an amplitude of 1, so it starts at the point 0, 1. Now, with a period of pi, what that means is that it's got to get back to that cosine value of 1 over here. And so I'm going to start thinking about my quarters, or what kind of happens. Well, halfway between my period on cosine, as I'm moving from peak to peak on my cosine, halfway between there, I've got my valley point. So I've got this point of -1. And then halfway between my valley and my peak, I've got zeros. And then I can think about my quarters and kind of where they're occurring. It's a little bit weird with this graph scaled 3 between your pi over 2, so they're actually here. And I'm right now trying to say that this is one period of this cosine function. I'm going to stop and think. I'm going to see that, okay, I've got my quarter from my peak to my 0. I've got my next quarter from my 0 to my valley. I've got my my third quarter from my valley back to my 0, and then I've got this last quarter from my 0 back to my peak. It's all appearing over pi. They're all spaced out properly. I'm really happy with that. So I've now graphed it, and as opposed to actually plugging in values, going through the tediousness of trying to figure out how this works, I'm just thinking about the general shape and that general quarter phenomena. It's going to have to get back, again, to that positive 1 by 2 pi. Halfway between those positive 1s will be my -1. And then halfway between my -1 and my positive 1 will be zeros. And I'm going to be able to draw this cosinusoidal wave shape again. I'll make that one a little bit better. And there you have it. That's how I go about doing my period shifts, is I'm just trying to break it down in the quarters and kind of what happens in the general shape. So I just draw out a period, I draw where it has to return to, and then I start saying to myself, okay, what happens from the start to the first quarter to second quarter? And I'm going to do this with sine and cosine as well. So that's how you go ahead. That's how you do your period shifts. Don't worry, you're going to get a lot of practice with this over the next 2 class periods, and you're going to get like another review notes on this on Thursday. I'm going to go over this again in a little bit more detail to kind of help you with that. For homework, you've got a worksheet on Google Classroom. I actually have a video answer key for the entire worksheet. Since this is kind of a new and a little bit more of an abstract concept, I go over every single problem. So if you're ever confused, you can reference that video answer key. And then again, any questions or concerns, reach out to me sooner rather than later. I'm expecting this to be a little bit more difficult. This is something that I don't think is the easiest thing to learn through videos. So please, please, please email me, set up an appointment time. We can meet whenever. Have a great night.